The theory of differential equations dates back about 350 years to the discovery of calculus, that's differentiation and integration, by Newton and independently by Leibniz. At the same time, Newton discovered his three laws of motion which govern the way that more or less everything moves. And that was really his interest and his stimulus for developing the calculus. But if you look into Newton's Principia, you won't see anything that you'd recognise these days as an differential equation. And it took Leibniz to come up with the dy by dx notation that's so familiar. Since their discovery, differential equations have been applied to all kinds of examples, from the very smallest in the atom and quantum mechanics to the whole universe in Einstein's theory of general relativity. The kind of examples you come across as a student seem more everyday and often seem much more contrived. But even these seemingly contrived examples are situations that may actually have happened. One favourite of teachers and lecturers is the phenomenon of resonance, and they'll often talk about how armies have to break step as they march over bridges to prevent them falling down. Now, this isn't something that they've just made up, and it actually happened at a bridge just outside Manchester in Broughton in the 1830s. This is certainly a problem, and just down the river on the Albert Bridge there's a sign instructing officers to get their soldiers to break step as they cross to prevent this happening. Something similar happened here on the Millenium Bridge in London. This time though, rather than the bridge bouncing up and down and shaking itself apart, when the bridge was opened and people began to walk across, the bridge began to sway violently from side to side. The architects had obviously anticipated the fact that the bridge could bounce up and down, and there are springs and dampers underneath to make sure that that doesn't happen. But this swaying from side to side was a new phenomenon that they didn't expect. The problem is that essentially this is a psychological thing rather than a mechanical one. As the bridge started to sway, it was the people themselves that started to sway in sympathy with the bridge that produced the problem. As the bridge swayed more and more, the people swayed more and more, and the whole bridge began to swing from side to side. In order to get round this problem, as well as the dampers underneath to stop the bridge going up and down, there are now dampers called dashpots along the sides of the bridge to stop the bridge going like this. These dashpots are essentially cylinders filled with some sticky fluid and a piston. So as the bridge starts to move this way, the piston moves through the fluid and everything is damped down. So this damping effect stops the bridge swaying from side to side too much, and now people can come and go freely to and fro. Simple calculations with elementary differential equations show that now you might need about 2,500 people walking over the bridge at the same time in order to get this wobbly phenomenon.